So today I want to show you how to solve the initial value problems, a coupled initial value problem, which is taken from the example 5-7 from the Elements of Chemical Reaction Engineering 5 edition. And here's the setup of our differential equation. We have dx by dw and dp by dw, and p is the pressure ratio, which starts from 1 and until 0. So we're going to solve the differential equation from within the range of 0 until 27 kilograms of catalyst. So I'm going to start by defining the parameters, which are epsilon, epsilon is the expansion ratio of the gas, K prime, which is the rate constant for catalyst reaction, catalytic reaction, and FA naught, which is our feed flow rate. And alpha, which is a parameter for our pressure drop. Okay, so now that we have the parameters defined, I'm going to go ahead and define the differential equations. So first, I'm going to call function of dy, dx, and I'm going to name this function as my ODEs. And since it's a function, we have to pass in our variables and parameters. So here, we're going to pass everything from our weight, which is the x-axis, and y, which are the x and p. So since we're going to define our dy by dx, I'm going to say that x, which is our conversion, as y1, and p as y2. Okay. And so I'm going to say that I'm going to write this differential equation down. Okay. Since our dx by dw requires an explicit equation, which is Ra prime, I'm going to say it's Ra. Oh, sorry. This is correct. Okay, I 2p. Sorry. 1 plus epsilon x by 2p. Okay. And since we need the expression for RA prime, we're going to say that RA equals to minus, according to this explicit equation, k prime times 1 minus x divide 1 plus epsilon, 1 plus epsilon x, again divided by p. Okay, so now our RA is defined. Now we're going to go ahead and join these two ODEs and make it a set of ODEs. So I say that this is dy dx equals to dx dw with dp dw. Okay. So now to solve our ODEs, we're going to define the initial conditions, which is, of course, we know that x starts from 0, and p should start from 1 because p is equal to p naught. And we say that we're going to solve the ODEs from 0 to 27 kilograms of catalyst. So W range is 0 and 27. Okay. So our results, W, which is the x-axis, and y, which are x and pressure ratio, equals to, using ODE 45, function of weight and y, since y are x and p. So I'm going to solve my ODE and basically just copy the variables from here. And what we do next is we have to define the span, which is the range, t-span or range. So the range. And we also have to define the initial conditions. Pass in the initial conditions. Okay. So now I think our solution is set. We can go ahead and run. Okay. Okay, so now we can say that the solutions are given okay, sorry. Initial conditions. So initial conditions, we say that P0 equals 1. We can just go ahead and put 1, or we can define it elsewhere and pass in the value. So I say P0. Okay. Okay, so now the results are in. We see that the this is the our W, or the x-axis, and these are the results. And basically on this column, in this column, we have the conversion, and we have the pressure ratio on the second column. So just now I forgot to define the RA and F outside the function, so that we can plot it. So I'm going to define the RA the same way, except for I'm going to use y1 and y2 when it's outside the function, because outside the function x is not defined. So okay, I'm going to I'm going to go ahead and define the rate, which is the negative RA prime. So the same way, without the negative sign, but we're going to replace the x and p with y1 and y2. And the reason why I'm writing y1 and y2 like this is to calculate using the entire column. Okay. Okay, now we can go ahead and plot. So I'm just going to copy my plot from another code. And so basically I want to plot the XP, F, and rate. Okay. So first we'll go ahead and plot the X. So we say that it is Y colon 1. Okay. Okay, so here we have the conversion profile along the catalyst weight. Also, we'd like to plot the pressure ratio, which is Y2. Okay. And next is our velocity ratio. So here we can see the conversion profile, pressure ratio profile, and velocity ratio profiles. And to plot the reaction rate, I'm going to create another figure. Go ahead and plot. Our rate. Okay. So thank you for watching, and I hope you can learn how to solve an initial value problem, a coupled initial value problem using MATLAB.